Yes, good afternoon, dear students.
Good afternoon, ma'am.
Good afternoon. So, in yesterday's class, okay, so we have just revised everything again. So, we were discussing about the Daniell cell, right? Daniell cell, then we have discussed about the salt bridge. So, we have seen the function of salt bridge, what is electrode potential, right? Then we have also discussed about the oxidation potential and reduction potential. Then we have studied about the standard hydrogen electrode. So that is SHE. It is used as a reference electrode. Okay. Then based on that, we have also discussed how to calculate the EMF of the cell. So EMF of the cell can be calculated as E cathode minus E anode. Okay. So then, okay, so this is the working of the Daniell cell, right? Then we also have studied about the electrochemical series. So these were the electrochemical series. Okay, so electrochemical series, how they have arranged? They have arranged in the decreasing standard reduction potential values. Okay, so you can see hydrogen here. Okay, the platinum electrode, which is dipped in the HCl solution. Okay, so this EMF of the cell will be 0. Okay, at standard conditions. Okay, so here, so the atmospheric pressure is 1 atmospheric pressure at 25 degrees Celsius. Okay, at 1 molar concentration of HCl, what will be the EMF of the cell? It is 0. So you can see the values which are the metals which are placed below the hydrogen. Okay, so all are having negative values. Okay, so more the negative value, it means it is a stronger reducing agent. Okay, and above 0, you can see the positive value. So more the higher the positive value, okay, so stronger is the oxidizing agent. So remember that. Okay, fine. So these things we have discussed. Then we were supposed to discuss about the Nernst equation, right? We were supposed to discuss about what? Nernst equation. So let us start with the Nernst equation. So what does Nernst equation tell you? So Nernst equation, it tells you mathematically it represents the electrode potential of an electrode. Okay, or the cell potential of an electrochemical cell with their standard states. Okay, with their standard states at different concentration and temperature. So any electrode potential of any electrode. Okay, so the electrode potential of an electrode at any concentration, it is measured with some reference electrode. So which is our reference electrode? It is SHE, that is standard hydrogen electrode. So whenever you want to calculate the EMF, that is the electrode potential of any electrode, so that time, oh, okay, which is of any concentration. So what you need a reference electrode. So that reference electrode is what? It is your SHE. Okay, that is standard hydrogen electrode, right? So let us see the equations. Okay, so here you can see that. So here you can see, okay. So Nernst equation is very important for 2 marks. Okay. So what it tells you? It tells you about the relationship between the electrode potential and the concentration of the electrolyte. Okay. So how the reaction is given as, so Mn plus. Okay. So concentration of the concentration of the solution, it can be expressed as M N plus, which is aqueous, plus electrons. Okay, electrons are taken. So it is a reduction. So this is a reduction, gain of electrons to give you Ms. Okay, that is your metal. Right. Now here, this is in oxidized state. This is said to be in what? This is in oxidized state, and this is in its reduced state. Okay, it is in its reduced states. Right. Now here, the Nernst equation for this reaction. How do you write the Nernst equation? So that is the electrode potential. Okay, it is given as Mn plus by M. Okay, is equals to E naught of. E naught means the standard potential. Okay, standard electrode potential of Mn plus by M minus RT by NF. RT by NF. Okay, then log of concentration of M. Okay, that is your on the right hand side. that is of your electrode upon Mn plus. Okay, that is your electrolyte. So this is the equation what you get. Now after solving this, okay, so E, okay, that is the electrode potential can be given as E naught minus, okay, what is R value? R value is 8 point, okay, or I'll write it like this. So it is minus 2.303 RT. Okay, so we are taking the standard. So we are going to introduce here the 2.303, okay, by NF log of concentration of M, okay, that is electrode by concentration of the electrolyte, okay, which is like this. So now the concentration of this metal, okay, the concentration of the metal, it is taken as what? It is taken as unity. Why? Because it is in pure, okay, it is a pure solid. So, okay, it is a pure solid, or, okay, it can be a pure liquid. So it is taken, the concentration is unity. So E is equals to E naught of minus 2.303 RT, okay, then NF log of, okay, log of 1 by Mn plus, because we have taken the metal as one unity. Okay, now what we do, we take the Mn above. Okay, if we transfer it above, so how it will be? So E is equals to E naught, okay, plus 2.303 by Nf, okay, log of Mn plus. Okay, so this is the equation. So you can use this or this equation for calculating the Nernst equation. So what are the values here? So let us see the values. So E, what is E? E is the electrode potential of the cell. Okay, this E, it represents your electrode potential of the cell. Then E naught, E naught represents what? It represents the standard electrode potential. What is R? R is your gas constant. Okay, the value of R gas is 8.314. 8.314. Then F represents what? Faraday constant. That is 96,500. Okay. Then Faraday's constant. Then temperature. Okay. T is the standard temperature. Okay. So it is 298 Kelvin. That is 25 plus 273. So that is 298 Kelvin. So Faraday is this, right? Then what? So N, what does N represents? N represents the number of electrons which are gained during the electrode reaction. Okay, so on substituting, now let us substitute these all values in the above equation. So what we get? So E is equals to, okay, so E is equals to E naught plus, okay, 2.303 into 2.303 into R is 8.314 into temperature is 298 divided by N into 96,500, okay, and log of Mn plus. So what you will get? So you will get E naught plus 0.0591 by N log of Mn plus. Okay, so remember that for standard electrode, okay, for standard electrode, we know that the concentration, okay, concentration of the electrolyte will be 1. Okay, so if we put the concentration of Mn plus as 1, so what will be the value? So it will be E is equals to E naught, because so this into this will be 1 only. So this whole value will become 1. So E will be equal to E naught. So for standard electrode, so E will be equal to E naught. So the value will be, okay, so this is with respect to your Nernst equation. Very important. Nernst equation is very important. Okay, so problems are also there on Nernst equation. So we'll be solving that. So here, okay, Nernst equation for a electrochemical cell. So here, so for an electrochemical cell, okay, A of A plus B giving you C of C plus D plus D, where the number of electron exchanged will be N. Okay, it is represented by N. Then if you write the Nernst equation, how do you write the Nernst equation? So Nernst equation can be written at electrode potential of the cell is equals to E naught of cell, that is the standard potential, is minus 2.303 RT NF log of QC. QC means what? Products, the concentration of products upon concentration of reactants. So here in the second step, they have written C. Okay. So here it is written. Okay. Now here we know that 2.303 RT by NF. Okay. The value comes to 0.059 by N. Right. So put this value here. Okay. So E naught of cell will be equal to what? E naught of the cell will be equal to that is EMF of the electrode potential of the cell is equals to E naught of the cell minus 0.059 by N log of reactants upon products upon the reactant. So in general, how we can write? So in electrode potential of the cell is equals to E naught of cell minus 0.059 by N log of QC, where QC is what? It is your quotient. Okay, it is a quotient, and quotient is given by products by your reactants. Okay, so Nernst equation, it is given like this for any electrochemical cell. So you have to write it in this form. Understood? Yes. So please note this final equation. Okay. So please note this final equation where QC is what? QC is your quotient. Okay, quotient, and it will be the products upon your reactant. Okay, products upon your reactant. Okay. Let us go to front. Okay, problems we will do at the end. Okay, problems we will do at the end. So now when we are just relating the Nernst equation and equilibrium constant. Okay, Nernst equation and the equilibrium constant. So let us see what is equilibrium constant now. Okay, so equilibrium constant at equilibrium. Okay, whenever any reaction is proceeding, suppose AA plus BB giving you CC plus DD, right? A reaction is proceeding. So that time when it reaches the equilibrium, okay, when it reaches the equilibrium, when half of the products are converted into, half of the reactant is converted into products and half of the products are converted into reactants. Okay, so when it reaches the 50% reaction, so that time what happens? What happens when it comes in equilibrium? There will be no net electrons will be flow. So no electrons will be flown. Okay, so it will be equal at that moment, right? So what will happen that time? So QC, that is your quotient, will be equal to Kc. Kc is your equilibrium constant. Okay, and E naught of cell, that is the electrode potential of the cell, it is represented by 0. How it is represented? It is represented by 0. Okay, so we know that. So we have the Nernst equation. So that is E naught of the cell minus 0.0591 by N log of 1 by Mn plus, right? So this is our Nernst equation. Now if we use the form these all things, okay, so we know that at equilibrium what will happen? No net electrons will be flown in the electrochemical cell. Okay, so there won't be any electrons which are flowing, so there will be 0 electron flow at equilibrium. So the time QC will be equal to Kc and E naught of the cell will be equal to 0. Now, so if you put these values in the above reaction, so E of cell is what? It is 0. So let us put the value as 0 only. So let us put the value as 0. So 0 is equals to E naught of cell minus 0.0591 by N. Okay, by N log of 1 by, this is what? So that is represented by log of QC, right? It is represented by log of QC. QC is equal to Kc. So we will take log of Kc. Okay. Now E naught of cell is equals to what? So if I transfer it here, so this will become plus, right? So it will become plus 0.0951 by N. Okay, log of Kc. So when you are calculating the when you are relating the Nernst equation with the equilibrium constant, so standard electrode potential of the cell is represented as 0.0591 divided by n log of Kc. Okay, divided by n log of Kc. So this is the answer. Okay, so this is the answer. So, like this, we are going to find out the equilibrium constant. Okay, so equilibrium constant, how it is related to Nernst equation. So, like this. Okay, so we know that at equilibrium, what will happen? There won't be any electron flow. So, we consider it as zero. Okay, so at equilibrium, what will happen? The quotient, that is the products upon the concentration of products by reactant will be equal to the your equilibrium constant. Okay, and potential of the cell, electrode potential of the cell will be equal to what? It will be equal to 0. So we know that electrode potential of the cell is equals to E naught of the cell minus 2.303 RT by NF. So we know the value of 2.303 into RT by NF is equals to 0.059 by N. So log of QC is equal to KC. So after substituting the final answer, you get it this. Okay. So E naught of cell is equals to 0.059 by N log of KC. Okay. So next is the relationship between free energy change and equilibrium constant. Okay. So next we are going to see the relationship between the free energy change and equilibrium constant. So free energy change, it is also called as what? It is also called as a Gibbs energy, right? It is also called as a Gibbs energy. That is standard Gibbs energy, right? So now here, so whenever any spontaneous process is occurring, okay, whenever the spontaneous process, what will happen to the free energy? The free energy of the system, it goes on decreasing. Okay, it goes on decreasing. So what will happen? This decrease. So this decrease in the free energy, what will happen? It will be equal to the maximum useful work done in a spontaneous process. So whatever the free energy is getting decreased. So this free energy is equal to the useful work done in the spontaneous process. So it is given as delta, that is G is equals to work done. Okay. So whatever, because it is decreasing, the free energy is decreasing. So we are taking minus. So minus of delta G, that is your free energy is equals to work done. So work done, that is a useful work done on the system. So this can be given as 1. Now during the galvanic cell, so we know now galvanic cell, what will happen? The work done during the transfer of NF coulomb of charges across the potential E. That is now when you are, the galvanic cell is there. Okay, whatever the work done during the transfer of electron, that is NF coulomb of charges. When you have NF coulomb of charges across the potential, okay, across a potential difference of E volts, it is given as what? It is given as the work done is equals to charge into PD. Okay, charge into potential difference. Charge is what? Charge is NF. Charge is NF into potential difference is what? Potential difference is E volts. Okay, so this is the second step. This is the second step. So when you relate the equation 1 and equation 2, so delta G is equals to minus delta G is equals to NF into E of cell. Okay, so at standard condition. So when you have standard condition, so what will happen at standard condition? So at standard temperature pressure condition, so delta G naught is equals to NF minus NF. Okay, I'll transfer that minus sign on the right side into E naught of cell. Okay, so this is the standard what the relationship between the free energy and the equilibrium constant. So let us see the relationship between the this. Okay, so this is your standard free energy. So standard free energy, it can be calculated as what? Delta G naught is equals to minus NF into E naught of cell. Okay, now next is we are going to relate it with what? Now we have found out the free energy. Now let us relate this free energy with what? Your equilibrium constant, right? So we got the free energy. So free energy is what? It is the decrease in the free energy. Okay, so the free energy, what will happen on the system? It decreases. Okay, because and it is equal to the useful work done in the spontaneous process. Okay, so delta minus delta G is equals to work done. Okay, so minus delta G is equals to work done. So what is the work done? Work done is nothing but the charge, number of charge passed, okay, through across the potential difference of E volts. Okay, so that we have put and we have got the delta at standard condition. We have got the value of your free energy. Now let us relate this with your equilibrium constant. So we know that E naught of cell, okay, it is a thermodynamic quantity, and delta G, okay, delta G naught, it is what? It can be calculated. So from this equilibrium constant relation, that is delta G naught is equals to minus RT by ln of Kc. Okay, so we know that NF. So NF is equals to nothing but it can be your, just here. So delta G naught is what? Delta G naught is your free energy. Okay, standard Gibbs free energy. It is standard Gibbs free energy. So G naught of cell is equals to what? 2.303 RT NF log of Kc. Right. So this is a relationship between the standard electrode potential and the your equilibrium constant. Now E naught of cell is nothing but your NFE. NFE of the cell. Okay. So is equals to 2.303 RT log of Kc. So what I've done, I've transferred these here. Okay. Now NFE cell. What is NFE cell? So just now I got delta G naught is equals to minus what? Just a second now. Minus NF into E naught of cell. Okay. So here what we will get? So delta G naught is equals to minus NF naught into E naught of cell. So what I'll get now? So delta G. So NF of E naught cell is nothing but your G naught. So what is there here? Negative sign. So negative I am transferring on this side. So it will be 2.303 RT of log of Kc. Because we know that, okay, so this is the relationship between the Gibbs free energy and your equilibrium constant. Okay, so like this, we are going to get the relationship. Now, whenever you have a spontaneous reaction, so what will happen to the free energy? It will be negative, and the electrode potential of the cell will be positive. So the type of cell is galvanic. The type of cell is what? A galvanic cell. Okay, it is a galvanic cell. So whenever you have a spontaneous reaction, reaction, okay, so delta G naught is negative. Okay, delta G naught is negative, and your E naught of cell, that is your standard electrode potential, is positive. So type of cell is galvanic cell. Now, whenever you have a non-spontaneous reaction, so the time what will happen to the delta G naught? It will be positive. Delta G naught is positive, and what will happen to the E naught of cell? That is a standard electrode potential. It is negative. The type of cell is the electrolytic cell. And whenever you have a equilibrium, so it will be a dead cell. Okay, because no electron transfer takes place. So, right, equilibrium is the net charge will be zero. So, there will be zero itself. So, it is a dead cell. Okay. So, numericals we will be solving at the end. Okay. So, let's solve the numerical at the end. So, we have seen now what is conductance, right? What is conductance? What is resistivity? So, I'll just read it out. Conductance is what? Electrolytic conductance. It is the ease of flow of electric current through the conductor. Okay. And it is a reciprocal of resistance. So 1 by R. What is conductance? Conductance is given by G. So 1 by R is nothing but it is a conduct. Okay, it is a reciprocal of resistance. So the unit of ohm, that is your conductance is what? Per ohm. The this what the unit of resistance is ohm. Okay, so it is inverse here, so it is per ohm. Okay, or it is mho, or it is Siemens, or it is per ohm, like this. Okay, so this is Siemens. Okay, so these are the symbols. So these are the symbols. Okay, so per ohm, mho, and Siemens. So this is the unit. Okay, this is a unit of conductance. Next is resistance. Resistance is what? Resistivity of a conductor is its resistance of 1 centimeter length and having a area of cross section to 1 centimeter square. So resistance is given as, okay, rho into 1 by A. So rho is equals to 1 by A. So rho is what? Rho is equals to R into A by 1. So what is the resistivity? So resistivity is this. So it is ohm centimeter, or okay, or it is given by ohm centimeter. So this is the SI unit of resistivity. So this is the SI unit of resistivity. Okay. So like this, we are calculating the what? Its uh, units. Okay, like this, we are calculating the units. Okay. Next is conductivity. Next is what? Conductivity. So conductivity can be calculated, okay, as the conductance of a solution when it is placed in two electrodes, okay, between the two electrodes of 1 centimeter apart and having 1 square meter as the area of cross section. So this also we have discussed. How is the conductivity of a solution calculated? Conductivity of a solution, it can be calculated as the conductance of a solution, okay, which is placed between the two electrodes of 1 centimeter apart. So here you can see, so here there are two electrodes, okay. These are two electrodes, so these are two different types of conductivity cell. So here you can see these are two electrodes in uh, a round bottom, like this is the flask is there, right? So here you can see that the solution, okay, the electrolyte is placed here. This is the electrolyte and these are the two platinum electrodes, okay. The platinum electrodes, they are connected to the connecting wires, okay, and they are placed between the two electrodes of 1 centimeter apart, and they have an area of 1 centimeter of the area of cross section. Okay, so area of cross section is 1 centimeter, a square centimeter. So the conductivity is the conductance of 1 centimeter cube of a solution of an electrolyte. So conductivity is the reciprocal of resistivity. Conductivity is reciprocal of resistivity. That is a reciprocal of resistivity. Okay. So it is given as K is equals to 1 by rho. Okay. So K is equals to 1 by R. That is rho is nothing but 1 by 1 by A by 1. Okay. So after you get it, so it is the cell constant. So calculating the, so this is another your conductivity cell. Okay, you can see one more conductivity cell here. So in the same, okay, in one beaker there are two platinized platinum rod, okay, and there is two connecting wires, okay. So conductivity of the solution can be calculated like this. So we have seen what is conductivity, molar conductivity, okay, molar conductivity. Okay, so next we'll see the factors. Okay, what are the factors which are affecting the conductivity of a solution of electrolyte? Okay, so first is the nature of electrolyte. So the strong electrolytes, so we know what are strong electrolytes and what are weak electrolytes. So whenever you have a strong electrolytes, like your potassium nitrite, when you have potassium chloride, so when you put in water, okay, when you put this ions into water, what will happen? This will dissociate. What will happen to the ions? They will completely get dissociated. Okay, and these ions, okay, these solutions will have a higher values of molar conductivity. Okay, the value, it will be more. So what will happen? Whenever you have a stronger electrolytes, the conductivity value will be more. Okay, and whenever you have a weak electrolyte, suppose again when you have a weak electrolyte, like suppose acetic acid, okay, barium hydroxide, so when you add in water, what will happen? They will ionize or they will get dissociated to a smaller extent. Okay, they will not get completely ionized. They will get ionized at a smaller extent in aqueous solution. And what will happen to the molar conductivity values? The molar conductivity values will be less. Okay, the molar conductivity value, it is what? It is lower. Okay, so it is very less okay, so this tells you about the nature of electrolyte. So whenever you have strong electrolyte, what will happen to the ions? They will get completely dissociated because they completely get dissociated in the water. Okay, so high amount of ions are present in the water. Because of that, the value, molar conductivity value will be more. And if you have a weak electrolyte, what will happen? The weak electrolyte, they will not dissociate completely. They'll not get dissociated, okay, completely, or they do not get ionized completely. So it is having very less or lower degree of ionization. Okay, so they will ionize at a very less extent. Okay, so because of that, what will happen to the molar conductivity value? The molar conductivity value will be less. Okay, it will be less. Fine. Okay. So next is the concentration. Second factor which will affect it is the concentration. So the concentrated solutions of strong electrolytes have significant interionic attraction. So whenever you have strong electrolytes, so the ions, okay, they are associated with the positive interaction. Okay, sorry, attractive. That is, they are having a this forces. Now see, suppose I have a KCl solution. Okay, KCl's this I am adding in water. Okay, what will happen? Okay, what will happen in the beaker? So I have water molecule and I have the KCl. So KCl will get associated into K plus ions and Cl minus ion. Okay, K plus ions and Cl minus ion. Now what will happen? Because this is a strong electrolyte, okay, these interionic interactions, okay, this will be more. The concentrated solution, what will happen? The strong, because of the strong electrolyte, okay, what will happen to the inter-ionic interactions? It will reduce the speed of ions. And what will happen to the molar conductivity value? The molar conductivity value will be less. Okay, molar conductivity value will be less. So So what will happen? So the concentrated solutions, okay. So when we are talking about concentrated solutions, so because of its interionic attraction, they will reduce the speed. Okay, they will reduce the speed of the ion. What will happen to the speed of the ion? The speed of the ions will be reduced. Okay, the speed of the ions will be reduced. And what will happen to the value? The value of molar conductivity will be lower. Now, as the dilution decreases, okay, as the dilution decreases, okay, what will happen? Such interaction and increases the value of this. So, as the dilution decreases, means what? As you are putting more and more, as you are means what? As you are putting more and more water to the concentrated solution. what will happen? The attraction forces will decrease. Okay, attraction forces will decrease because you're decreasing or you're diluting the solution. Because of dilution, what will happen? Because of the interionic forces will go on reducing, and because of that, the value, that is a molar conductivity value, will be more. Okay, so this is another thing about concentration. So concentration also plays very important role. So because of strong electrolytes, what will happen? Because of strong electrolytes, there will be strong interionic attractions. Okay, because of interionic attraction, the speed of the ions will be slow, because the forces are hard, right? The stronger the forces, the movement will be very slow, right? They are holding them very tightly, so the movement of the ions are not very fast, right? So K plus and Cl minus ion, if they are present, because the forces of attractions are stronger, so they are not able to move. Because of that, the speed of the ions are reduced. Because of that, the this what because of that, what happens? The value of molar conductivity will be less. Okay. Now, as you're putting more and more water, as you're putting more and more water, what will happen to the concentration of the solution? The concentration of the solution will be decreasing. Because of that, the speed of the ions will increase, and the value of the molar conductivity also increases. Okay. So this is the another factor. Okay. So let us see next one. Okay. So these were the two different factors which are what affecting your conductivity. Okay. So this is the affecting your conductivity. Okay. So next we'll see the variation. Okay. We will see the variation of molar conductivity with concentration of solution of weak electrolyte. Okay. Now suppose in case of weak electrolyte. So now we are considering a weak electrolyte. So weak electrolytes. So what will happen to the weak electrolyte? The degree of ionization. What will happen to degree of ionization? It will increase with dilution. Okay, it will increase with dilution. So because of that, what will happen to the molar conductivity value? Molar conductivity value will be increasing. Okay. So when you have a weak electrolytes, so what will happen to weak electrolyte? So molar, so remember that, so remember this point, that molar conductivity, when we are discussing about molar conductivity, okay, so this molar conductivity, it will increases, okay, it increases with decrease in concentration. It will increase with decrease in concentration. That is, as you are diluting the solution, what will happen? As you are diluting the solution, the speed of the ions will reduce, right? Speed of the interactions will be reduced. Because of the interionic interaction is reduced, the speed of the ions will reduce. Because of the speed of ions are reduced, what will happen to the conductivity of the ions? Conductivity of the ions, that is molar conductivity, will be more. Okay. So because now suppose on dilution, okay, now we are having a volume of solution. Okay, there is a amount of solution which is 1 mole of electrolyte. Okay, which you are having 1 mole of electrolyte. So what will happen? The molar conductivity, as it is decreases with the increase in the decreases in the concentration. This is because on dilution, the volume of a solution which is containing this 1 mole of electrolyte, it will increase. Okay, it will increase. So what will happen? The increase in this volume. So this volume increases is much more than the decrease in the conductivity. So because of that, as the volume increases, what will happen? The molar conductivity also increases. Okay. So this is according to one law that is called as the Kohlrausch law. Okay. So let us see. So here, now KCl, you can see this is a KCl. It is a strong electrolyte. Okay. KCl, that is a potassium chloride. It is a strong electrolyte. So, so what is done? So two solutions are taken. One, okay, in one beaker, your KCl is added. That is your strong electrolyte is added into water. Okay, in aqueous solution. In another, you are having weak acid like acetic acid. You are adding in water. So because as it is a strong electrolyte, okay, because the interionic forces is more, okay, the what will happen to the speed of the ions? The speed of the ions will be slow. Because of that, the conductivity value. What will happen to conductivity value? It goes on decreasing. Okay. Now, suppose you have a this what weak electrolyte. Now, weak electrolyte. What I have done to weak electrolyte? I am diluting the weak electrolyte. So because of what will happen to the this acetic acid? Okay, acetic acid. What is happening? Because the ions. Okay, after adding in water, the ions are weakly attracted. Because of that, the speed of the ions is more. Okay, so it is goes on. Okay, the speed of the this it goes on increasing. Okay, so because of that, what will happen to the molar conductivity values? It will go on increasing. Okay, so because of that, your delta, you can see here. Okay, you can see here what is happening. So this is limited. Okay, so this is in the straight. So okay, so from 400 to 200, so you can see the conductivity values. So conductivity values is same. Okay, it is going on the same path, right? So this cannot be obtained by extrapolating the graph. So the limiting value, that is delta, not m for weak electrolyte is obtained from Kohlrash's law of independent migration of ions. So this is obtained by Kohlrash's law. So very important for 2 marks. Okay, what is Kohlrash's law? Okay, so what is Kohlrash's law? At infinite dilution, okay, at infinite dilution, the limiting molar conductivity of an electrolyte is the sum of the limiting ionic conductivity of all the cations and anions. So this is the your what? This is your uh, Kohlrash's law. Okay, at infinite dilution, the limiting molar conductivity of an electrolyte, it is what? It is the sum of the limiting ionic conductivities of all the cations and ions. Okay, so this is about the Kohlrash's law. So example, okay, so this is a reaction where you can see that AB, okay, AB is the electrolyte, okay, AB is the electrolyte. So this upon dissociation, it is giving you X number of A and Y number of B. So when you are writing the Kohlrash's law, so it is represented as A of X, B by Y is equals to X of delta naught by AY and Y of delta naught by B. Okay, lambda naught by B ions. So for weak electrolyte, so example is given. So acetic acid, when it dissociate into acetate ions and H plus ions. Okay. So delta naught of M of acetic acid is equals to delta naught of acetate minus delta naught of H plus ions. Okay. So this is about your weak electrolyte. Next is variation of molar conductivity with temperature. Okay, that is molar conductivity with temperature. So the increase of temperature, what will happen if you increase the temperature? Okay, now you have strong electrolyte, you have a weak electrolyte. Now what will happen when you are increasing the temperature? What will happen? It decreases the interionic attractions of ions, okay, of an electrolyte. So because you are increasing the temperature, the interionic attractions will go on decreasing, okay, in the solution of the electrolyte. And what will happen? The kinetic energy, the speed of the energy, it will increase. Okay, so because you are increasing, we know that now. So as you are increasing the temperature, the interionic force of attraction, it goes on decreasing. As the interionic force of ions decreases, what will happen to the speed of the ions? It will increase. Okay, and what will happen to the molar conductivity? Molar conductivity will increase, right? This is with respect to the temperature, the variation of molar conductivity with temperature. Now, so if we define the molar conductivity of the weak electrolyte at infinite dilution, it is given as what? Delta M of acetic acid is equals to, okay, so that is your, okay, sodium acetate plus HCl minus NaCl. Okay, So NH4OH. So how do you calculate the NH4OH? So NH4OH, so NH4Cl plus NaOH minus NaCl. Okay, you get NH4Cl. So if you want to determine the molar conductivity, okay, so like this, by applying the Poldrash's law, you can get the following data. Okay, now for determining the degree of dissociation of an electrolyte, so degree of dissociation can be calculated as molar conductivity at a concentration C divided by molar conductivity at infinite dilution. So that is molar conductivity, degree of dissociation is given as molar conductivity of concentration at M and the at infinite dilution, that is delta naught lambda naught of M. Okay, so this is about your degree of dissociation. Okay. So next is about the electrolytic cell. Next is about the electrolytic cell. Okay, electrolytic cells and electrolysis. So in an electrolytic cell, what is done? An external source of voltage is used to bring about a non-spontaneous chemical reaction. So what we are doing in electrochemical cells, we are applying a external voltage. Okay, an external electrical energy is applied so that we can undergo a non-spontaneous chemical reaction. Okay. So what is this electrolytic cell? So electrolysis is nothing but decomposition of electrolyte. So this electrolyte, it gets decomposed. Okay, it gets decomposed. Okay. So when electric current is passed, so when you pass the electric current, okay, when you pass the electric current, what will happen? The dissociation or decomposition of electrolyte takes place. Okay, so either it will be in the aqueous state or in the molten state. So what is happening in the electrolytic cell? Okay, so for non-spontaneous reaction, you always require an external energy. Okay. So without external energy, without you put external energy, non-spontaneous reaction does not take place. Okay, you require an external source. For spontaneous reaction, you does not require an external source, but for non-spontaneous reaction, you require an this what you require an external source. So electrolysis, what is happening? The decomposition of electrolyte. So when you put the electric current, this electrolyte, okay, electrolyte, it will get decomposed. Okay, it will get decomposed. It is called as the electrolysis. So in the same electrolytic cell, okay, there will be one electrolytic cell. Means what? Electrolytic cell means we have seen. So you will have a beaker in the same. Okay, you will have two electrolytes. So okay, you will have two electrolytes. So an external source is there. An external source is applied. So what is there? So one impure. Suppose I have one impure copper rod. Another will be a pure copper rod. Okay, and I'll have a copper sulfate solution. So when you pass electric current, what will happen? So one is a anode, one is a cathode. So whatever the impure this is there. So from this impure copper, the pure copper will go and deposit on this pure rods upon external voltage. So in electrolytic cell, what happens? Both the external, that is oxidation and reduction, will takes place. So in the same cell, this both the reaction takes place. So anode is what? Anode is a positively charged. Okay, and cathode is a negatively charged. So at anode, what happens? Oxidation takes place, and at cathode, reduction takes place. So in case of galvanic cell, okay, in galvanic cell, which was the anode? Anode was a negative terminal. Okay, and at cathode, you had a positive terminal. So at anode, the oxidation could takes place, and at cathode, reduction takes place. Only the difference is that in galvanic cell, the anode was negative, and in cathode, it is a positive. Okay, so here it is vice versa. So during electrolysis, now, okay, when the electric current is passed, what will happen? The cations are liberated at cathode, and while anions are at anode. So positively charged at the anode and negatively charged at the cathode. So you know that like repel each other, and unlike charges, they will attract each other. So whenever the decomposition takes place, whatever the cations are present in the solution from the electrolytic solution, it will go and attach the cathode, which is a negatively charged, and the anions, okay, the negatively charged ions, they will go and attack the cathode, anode, which is a positively charged. Okay, so this is the electrolysis process. So during electrolysis, this is the process which it shows. Okay. So when two or more ions compete at the electrodes. So suppose when you have two or more ions and they're competing at each other. Okay, they are competing at the electrode. Then what will happen? Whichever the higher the ions which is having the higher reduction potential. Okay, we have seen now the electrochemical series, right? So whichever has the higher electrode potential values, it will get liberated at the cathode. Okay, and while the anion, which when the and the ion which is having the lower reduction potential value, that will get deposited at the anode. Okay, so depending upon the electrochemical series, also we have to see the migration of this ions. So suppose when you have two or more, okay, and they are competing with each other, so what you have to consider? You have to consider their reduction potential. So higher the reduction potential, it will get liberated at cathode, and lower reduction potential, it will get liberated at anode. Okay. So suppose what I have. So I'm doing the electrolysis. Okay, I'm doing the electrolysis, and my electrolyte is NaCl. Okay, I have a NaCl. So what I have done, so I have a beaker. Okay, I have a beaker. In this beaker, what I have done, I have taken a NaCl solution. Okay, I have taken a NaCl solution. And this NaCl solution, I have two electrodes. Okay, I have two electrodes. That is, these two electrodes are the graphite electrode. Graphite electrode means it is made up of carbon. Okay, it is made up of what? It is made up of carbon. So graphite electrodes are there. So graphite means it is an allotrope of carbon. So you have a graphite rod. You have a graphite rod or graphite electrodes. Okay. So what we have done here, so we have two electrodes, that is of graphite, and we have added a your NaCl solution. Now NaCl solution, it is an electrolyte, so it will go electrolysis. How it will go electrolysis? So upon passing the electric current, this NaCl, it will split into Na plus and Cl minus ions in the molten state. So in the molten state, what will happen? The NaCl, it will get dissociated into, or it will get it undergoes electrolysis at Na plus and Cl minus ions. So the reaction takes place at cathode and at anode. Okay, so at cathode, what will takes place? Reduction takes place. Okay, at negative terminal. So that is, reduction means Na plus plus one electron will give you Na solid, and at anode, that is your positive terminal, which is undergoing oxidation. What will happen? Cl minus plus, Cl minus, giving you half Cl2 gas plus electron. Okay, now take the overall reaction. Overall reaction is electron, electron get cancelled. So it is Na plus Cl minus, giving you half Cl2 gaseous plus NaS. Okay. So what you're forming? NaCl, okay, which is molten, undergoing electrolysis to give you Na plus and Cl2 at anode. Okay. So this is the electrolysis product. So whenever you have an electrolytic cell, so you have the two electrodes, same electrode, and it is dipped in the electrolytic solution. So this electrolytic solution, it undergoes electrolysis when you pass the electric current. Okay, when you pass the electric current, it will undergo electrolysis, and it will give you the reactions at cathode and anode respectively. Then you will write the overall reaction. Is it clear up to here? Yes. So the next reaction of NaCl of aqueous NaCl. Is it clear up to here? Yes. Okay. Fine. So this remaining conditions and things we will discuss in the next class. Any doubts up to here? Okay, fine. So we'll meet in the tomorrow's class. Okay. So go through whatever has been told. Okay. Just read it once. Okay. And if you have any doubts, you can come tomorrow. Fine. Okay. So I'll end the session here. Okay. So thank you.